Today we are going to study how liquids exert forces on objects that are immersed in them. Before that, we will define what is meant by a liquid according to us before we plunge into how liquids exert forces according to what objects are immersed in them. So that is item 2. Item 3, and I will show you how equilibrium plus some basic ideas about liquids tells us quite a bit about what happens. Liquids are materials that cannot sustain shear forces in equilibrium. You know what is meant by a shear force, right? So if you have an object that is like that, this is called a normal force, a force that exerts perpendicular to the object, and a force that exerts parallel to the surface is called a shear force. So in a liquid, this cannot be there if it is in equilibrium. So it cannot sustain it. That's what makes a liquid take the shape of the container, because if it doesn't take the shape of the container, then shear forces will come into play and it will slowly redistribute itself until it takes the shape of the container. At least it occupies that region. Okay, so examples of liquids include air and water, that kind of thing, which we are most familiar with, and we are going to be heavily looking at water. But that's not the only one. Oil is a liquid, molasses are liquids, shampoo, honey, etc. Anything that if you put it in a box and you wait for a while, it should take the shape of whatever container you're putting it. That's called a liquid. Okay, it may take a little bit of while, so until it becomes non-moving, it will be under dynamics. Once it stops moving, it's under statics. So then we know what it can do. Okay. When they move, they are all different, but surprisingly, all liquids are similar when they are stationary. And I will add some caveats here. It's not really that they are exactly same, they are similar. One of the ways in which we are going to utilize liquids is that we are going to assume that they are roughly incompressible. It matters because we will distinguish between air and water. Air is compressible, so it will occupy the whole box by expansion or compression. Water may not be able to occupy the whole box, so it has some surface. So this matters because in the cases of liquids which have free surfaces, you know what is meant by a free surface, right? It's not occupying the whole box, but there's some gap. In a free surface, then it turns out that gravity becomes a very important aspect to it. Okay, so that is the very key idea. So for liquids with free surfaces, gravity plays a vital role. So that's a very critical thing. So you gotta, and I will make it very specific for incompressible. So these are liquids that cannot be squished. Technically, you know, not everything can be squished a little bit. But for practical purposes, when I say incompressible, I mean under typical conditions. Very good. So we have agreed on all of this. So next we are going to look at why are we really interested in liquids? What's the big deal about it? And I'll show you that subsea situations really require a lot of liquids. So a lot of understanding of hydrostatics. So let us take a look at this particular example. This is from FMC Technologies, and you can see how their subsea platform works. First thing, notice the giant crane and the equivalent of the Christmas tree. So this is the thing that goes under the subsea platform, and you can see the cable systems. You can see why we actually ask you to study cable systems. So it's going to be lifted up. Right, there it goes. So you can see that there are 4 cables, not 3 as we do usually because of the symmetry that is involved. First thing, notice that this thing is not lowered over the side of the thing, but through the center of the barge. Part of the reason is because it's small enough for you to be able to do that. And the second thing is it's so heavy that if you put it on the side of the barge, you will really get lots of torques and moments that you want to avoid. So you want to keep this thing close to the center of mass. You can see the rover on the side that's descending along with it. So it's going to go deep into the water and you can see that it is going to be subjected to humongous water pressures. It's going to go all the way to the floor, and there it's going to sit on the pipe. There, it's now being attached. Okay, now you can see this tall pole with lots of objects attached to it. How come this is sent out the side? First of all, it won't fit in the barge. It won't fit in the central hole in the barge. Also, it's not that heavy, so you can use a side crane to do it. Now it's going to go down, and you can see that you have this cable system. So if you think that our cable problems are made up problems, they are not. They are actually representing some of these kinds of things. You can see the Y yoke type of thing that's hanging this particular rod. It's going to go all the way down. So you can notice how this rod is hung, right? So one of the cables is going to be removed by the rover ROV, the remotely operated vehicle, and it's going to tilt slightly because it's now not exactly at the center. You now you remember the problem that we gave you to do. This is what it is, this kind of thing, only slight tilt, but nevertheless it's done. It's lowered further down, and it's going to be attached there, right? So this rover is going to go attach that one first. Right? You got it, right? You will see that that first one is attached, and then the rover is going to go to the next one, and you can see why the tilt matters, so that I can attach it easier. So there, that is the, it's going to pull it. Everything is done through some kind of cable system because that's the most efficient way to do some of these things. It's going to get attached. And then you can continue, and you will see how it's completely locked. You can see the locking mechanism there. And then it's going to get detached, and off it goes. Okay, so I want you to understand that this entire thing is going to be under enormous pressure, because in many cases it is under more than 10,000 feet of water, and literally it's getting squeezed. Okay, so that's the idea. So this only perpendicular forces has some serious results. So in any static liquid, only normal forces on any surface immersed in it. So force vector is always along the normal to the surface. No tangential components to the force. So I want you to understand this again and again and again. So what happens is, here's this liquid region, and I have some object here, and once I put it in there, you can see that it has 1, 2, 3, 4 surfaces, and on each surface the force will be exactly perpendicular to that surface. Can you see that? That's it. The 4 surfaces will have forces which are exactly perpendicular to the surface. How much are these forces? So that's the next question. And it turns out that it's fairly easy to calculate by using basic ideas of just knowing what is the force of gravity. So the normal forces are not, it's not just one force. I want you to understand it's distributed, and again I'm mentioning it's perpendicular to the surface. Wherever it contacts, it's perpendicular. The magnitude of the perpendicular force per unit area is called pressure. So pressure is force per unit area, and it is to force, pressure is to force what density is to mass, right? And its unit is pounds per square inch, or PSI in the SI system, in the FPS system, or Newton per millimeter squared, or megapascals in the engineering, in the SI engineering units. You know, that's the typical units. In many cases, instead of using PSI, people will use kilopounds per square inch, KSI. What it measures is the intensity of the force, not the net force, intensity. If you want to calculate net force or net moment or something like that, you have to integrate. Okay, so please remember, units are important. What it means is force intensity. for pressure is to force, what density is to mass. Very good. So we now know what is meant by normal forces, distributed normal force. Now, very simple. If you have any object, surface, the vertical force on any immersed surface is equal to the weight of the liquid supported. What do I mean by that? So I have some region, and what I want to do is I want to find out how much is the vertical force supported by this piece. Okay. How much is the vertical force? Well, that's easy to do because I'm going to say that's surface 1, that's the other surface. We will not worry about that. So the thing is, the main motive force, once you have no motion, the thing that really wants to make this thing move is gravity. And so the weight of the liquid is this whole weight, that is the density times the volume occupied by the liquid, and it's acting down. What are the forces on the surfaces? Well, we just mentioned that the surface force Fh is a horizontal force on that surface. Fv1 is a vertical force from down. F slant is on the slant surface, and which makes an angle theta with the horizontal. And Fh2 is the horizontal force on this flat surface. Is it obvious to you that only the slant and the vertical force, these are the only two things that have to support the weight? These horizontal forces are going to do nothing. So because there is no shear on the walls, the entire weight of the water has to be supported by the bottom pieces. So if I do summation of forces in the vertical direction, I will get minus W plus Fv1 plus F slant sine theta equal to 0. So the net vertical force is Fv1 plus F slant sine theta must be equal to 8. So if you want to find out what's the net vertical force on this region, it's the weight, and it acts at the center of the column. It acts here, centroid of this region. Okay, what about the horizontal force? What about the horizontal force? If I want to compute the horizontal force on this, that's pretty easy. So I have the same object. Now summation of the horizontal forces will give us Fh2 plus F slant sine theta, which is this component, must be equal to Fh. So if you want to find the horizontal force on any surface like that, you just project it horizontally, and the force on this surface will be equal to the force on that surface. Isn't that amazing? So it's very simple. Okay, but the question is, how much is the force? I told you that the vertical force is weight, horizontal force is this, and all this stuff, but how much? How would I compute it? So let's go and we say, okay, fine. I got a surface like that with a small region that I want to look at. Again, calculus to the rescue. Just like we did for beams, we're now going to salami slice this thing. So I'm going to slice this piece out of this surface, and I'm going to look at it there. So there's the column of water and the weight of the water there coming down there, and as usual there's a force, pressure times the pressure, water pressure is acting there. How much? I don't know. That's what I want to calculate. And then this length is dx, that length is dz. So it's made a slice. So now just sum all the vertical forces and you will get summation of all the vertical forces. This length is dl, this angle is theta. So dl cos theta is dx. So if you want to calculate the total weight of the water column, it is integral, it is integral of force of gravity, gravitational acceleration g, times density as a function of z. Maybe it changes with density. You know, you might have layers. For example, very salty seawater will have a different density than pure seawater, that kind of thing. So density may vary as a function of z. Integrate g times density times dx will give you the total weight of all this water. And then pressure will be, upward force will be dl cos theta times pressure. P dl cos theta is upward force, is balanced by the weight, and the weight is this much. So you can see the pressure will be integral of rho z dz. If density is constant, it is rho gh. So pressure on a slant surface will be rho gh. Right? So irrespective of what happens, the pressure on a slant surface will always be rho gh. So it's always just equal to the weight of the water above it per unit volume. That's why you get rho gh. Okay, per unit surface area. So that's why you get rho gh. Okay. Now let's see what happens on a vertical face. So we did for slant face. I'm going to show you what happens to the horizontal and vertical faces. So we know what happens to the slant face. I want to know what happens to this face and that face. So what we're going to do is the following. The amazing thing is the pressure at a point on any surface is the same. So if you have an object, so here you have water here, and let's say I pick a point here and I put any surface through it, this way, that way, this way, whatever way I put, the pressure on this, no matter which way I put, will be the same. Now you wonder, is that something that you have to take for granted? No, you don't. You just have to realize that this comes from statics. So what I'm going to do is I'm going to take a small chunk. This is dl, this is theta, this is dy, dx, and I know that just now we computed the pressure is P1, this is P2 on this surface, and the pressure on this surface is P3, let's say. Now, summation of forces in the vertical direction pointing upwards positive gives me P2 dx minus P1 dl cos theta equal to 0, but dl cos theta is dx, so P1 equal to P2, so this pressure and this pressure will be the same. I've done some slight things. Actually I have to add to it the force of gravity on this whole thing, g times rho times dx dy over 2. That's the volume of this. If I take the limits and I let dy go to 0, this whole thing will go away and I'll get P1 equal to P2. That's the exact version. Same way if I do horizontal, I will get summation P3 dy negative plus P1 dl sin theta equal to 0. Again dl sin theta equal to dy, and I will get P3 equal to P1. Notice that the pressure on this face, that face, any face will be the same. This is what calculus will allow us to do. Okay, that's it. So no shear forces plus equilibrium implies that pressure at any point on any immersed surface is the same no matter how the surface is inclined. Pressure, remember, I'm not talking about force because force is integral of pressure, but pressure is force intensity. So force intensity only depends upon how deep it is, not upon which way the surface is pointed, and it will always act perpendicular to the surface at that point. So if I have a surface like that, the force intensity here is rho gh and it will act that way. The force intensity here will be rho gh again, but different h now, and it will act that way. Right? So that's all you need to know about fluid pressure. Thank you.